Teach me about the Great Lakes. Teach me about the Great Lakes. Welcome back to Teach Me About the Great Lakes, a twice monthly demonstration of my sheer incompetence when it comes to all things Great Lakes. My name is Stuart Carlton. I work with Illinois, Indiana, Sea Grant, and I am super pumped to be here on a Wednesday morning because I'm joined by my good friend, the one, the only Carolyn Foley. Carolyn, what's up?
There are actually a bunch of Carolyn Foleys in the world. I don't know if you ever Google yourself, but sometimes I see but anyway, yes, I am doing well. Thank you, Stuart. How are you doing?
I'm doing fine too. Yeah, there's a battle among the Stuart Carltons. That is true. And there's this one dude who lived in the 19th century, I think, named Hawking Stuart Carlton. It used to be when you'd find him. Since then, I've achieved enough in my career where I'm finally beating out someone who's been dead for 200 years when it comes to Google results for my name. So that's good. Anyway, so today, this is actually something that you brought up. I think it's near and dear to your heart as a Canadian American, or however you identify.
It should really be near and dear to the heart of anybody who's in the Great Lakes. And if you're paying attention to the news, you've probably heard about Line 5.
Line 5.
Yeah, and it's a really tricky issue because there are good reasons why it's there. There are concerns about why it's there. So today we're going to talk with somebody about some of the things. You probably need to take that back because I took over from you.
No, that's good. No, that's awesome. Yeah, we're going to talk to somebody about some things. That's what we do on this show. But the good news is today, the person we're going to talk to, as we all know, is a researcher, which means with apologies to our guest, it's time for the researcher feature theme. So here we go. Researcher feature, a feature in which a researcher gonna teach us about the Great Lakes. Our guest today is Dr. Eric Anderson. He is a hydrodynamicist, which reminds me of my first question. A hydrodynamicist with the NOAA Great Lakes Environmental Research Lab. Eric, how are you today?
I'm great. Thanks for having me. I'm glad to be here.
Yeah, thank you so much for coming on. So that is the first question. Hydrodynamicist. Hydro means water. Dynamism means having to do with movement or something, or maybe volume. So what is a hydrodynamicist?
Yeah, you hit it. So it's movement of water, kind of the physics of water. Maybe the reason that I use that term is to distinguish the stuff that I do from, say, works that hydrologists do. So hydrologists are generally interested in kind of quantity of water and movement of water, but in that kind of tracking water through the water cycle. Hydrodynamics is more about the momentum equations, the energy equations, so waves and currents and the forces behind what's going on out there, say, in my case, in the Great Lakes. So that's kind of the distinction there.
Sounds like super nerdy stuff. That's good.
That was a great answer, actually. I was super psyched.
I'm fired up. I'm I wish I were a hydrodynamicist. All right, that's good. So here we're here to talk about Line 5 today, which is so it's an oil pipeline. It runs under the Straits of Mackinac, right? And it delivers crude oil from Western Canada through Michigan and into Ontario. Is that how that works?
Yeah, it goes. So the origin is up in northern Canada. And then I don't know where it actually becomes technically Line 5, but essentially it runs from the western end of Lake Superior when we get into the Great Lakes region, so near Superior, Wisconsin, or Duluth, across the UP, right along the shoreline of southern UP, so along the northern end of Lake Michigan, and then it gets to the Straits of Mackinac, and it splits into two pipes at that point, dives down into the water. So when you hear under the Straits of Mackinac, it's in the water. It's not below the ground, but it rides along the bottom of the lake. And then resurfaces on the lower peninsula side of Michigan and makes its way to Sarnia, Ontario.
Great. And I said the Straits of Mackinac, didn't I? Oh my God, this day needs to end, and this just started.
you did, and I actually was going to call you out on that.
Yeah, but, you should. That's fair.
Eric was a lot nicer and just kind of said, "Oh,
I can't read and think."
So this fits in really well with you're a hydrodynamicist. You were talking about the movement of the water, and you mentioned that the the pipe is actually in the water when it goes kind of through that. Can you tell us a little bit about that area where the pipe is in the water and what the importance is to the broader Great Lakes in terms of water moving around and things like that?
Yeah, it's so I've heard it said by a colleague that it's the most dynamic area in the Great Lakes. Again, that word dynamics. But really, I think the reason he said that is the currents are wild there. There's a lot of movement, fast movement, that has, I think, been something noteworthy for people for a long time. We found, French explorers wrote about it in the 1600s when they were trying to go through there. And of course, Native Americans have been dealing with that for a long time before that. But essentially, the Straits of Mackinac connects Lake Michigan and Lake Huron. The way that I picture it, so first you have these two massive lakes, some of the world's biggest lakes in Michigan and Huron, connected by this very narrow bottleneck. The straits are about 5 kilometers wide, maybe at the narrowest point, and they're about 90 meters deep. So it's like an old river channel. When the lakes formed initially, Michigan kind of dumped into Huron through a riverbed. So at the bottom, there's this very deep, narrow river channel, and it's kind of like a V shape if you think of the transect there. But you have these two giant lakes, and whether the atmosphere is acting on both of those lakes all the time. So the way I picture it is if you could imagine two different water beds, that's the way I think about it, connected by some little, section that connects the two water beds. If you were to jump on one of them, all that water would rush through that little bottleneck into the other water bed. And that's what's going on in Michigan and Huron. So when the wind blows on one lake or atmospheric pressure is pushing down on one lake, it's forcing that water to move around. And when that has to go through the straits, you're now pushing, again, this massive amount of water through a small area. And so when it goes through there, it has to accelerate, and it moves much faster through that zone. So, which means the currents are a lot higher than what you see in the open lakes. It's almost like river currents, or if you want a visual picture of the water, the rapids, say, going over Niagara Falls. That's the speeds that you have going through the Straits of Mackinac at certain times when water's rushing back and forth through there. So it's an important area to navigation. If you want to get into Lake Michigan from any of the lakes, you got to go through the Straits of Mackinac. It's important in just movement of water from the Great Lakes to the ocean. So this is how Lake Michigan water gets, into Huron, down through Erie, Ontario, and eventually out to the Atlantic. But it's not just a one-way transaction there, because if you again go back to that waterbed analogy, which I'm not even sure I like that analogy, but we'll use that. But if you think about that, the water's going back and forth, right? It doesn't care which bed the wind is blowing on. And so it's not just Michigan water moving into Huron. That's the ultimate fate of Lake Michigan water. Lake Huron water is being pushed into Lake Michigan through the straits, and then maybe eventually back out. And even Superior water. So Superior drains down St. Mary's River into Lake Huron. Some of that water might be sucked through the Straits of Mackinac into Lake Michigan before it eventually makes its way back, down through the Great Lakes into the Atlantic. So it's really important to the way water moves through the Great Lakes, important to navigation. It's important to the tribes that have lived around that area for a very long time. It's important to tourism, and if you haven't been up there, it's just a beautiful spot. It really is awe-inspiring to look at the straits. So in a number of ways, it's important to a lot of the things we care about, and because it's so dynamic up there, that water that moves in and out of the straits really has a far reach, and maybe that leads into some of the reason why Line 5 has been such an issue.
So I just want to back up. So first off, the mention of waterbeds. I know you said you're not sure you like that analogy, but it instantly took me back to like when I was 7 years old, and I was like, man, these are so cool visiting my friends' house.
I'm not sure there are waterbeds anymore. I wonder that.
Oh no, my dad has a waterbed. In fairness, it's been in his room since he moved into his current house in like 1992.
It's still there. But yeah, so I just wanted to say, like a couple of years ago when I was starting it, we were trying to find some facts about Lake Michigan. And one of the facts we wanted to talk about was like the amount of time that a droplet of water hangs out in Lake Michigan.
Oh, wait, do you know this?
Well, I mean,
Because I can do the thing.
no, we shouldn't do a thing.
No, we got a thing. Here we go. It's a Great Lakes factoid. A Great Lakes factoid. It's a great factoid about the Great Lakes. Cha. Carolyn, what's your Great Lakes factoid?
My Great Lakes factoid is that it's either the amount of time, and Eric's going to correct me on this, the amount of time that a droplet of water hangs out in Lake Michigan is either like 97 to 99 years or 66 years or something like that, right? Because the modeling, like you think that like, okay, down around Chicago, stuff is sort of hanging out there. But when you, like, people didn't necessarily think about everything that's happening at the Straits. That's like the water's coming back and forth and splashing all over the place. So Eric can correct me if I said either one of those wrong, because when I went looking for it, I found multiple answers that were really different. I was like, what the heck?
Yeah, I don't have those numbers could be right. I don't have not the top of my head, but I think what that calculation is based on, the numbers I do have in my head. So like the net flow from Michigan to Huron is something like 1 to 2,000 cubic meters per second, like an annual net like movement of water from Michigan to Huron. But the Straits moves water back and forth at like 80,000 cubic meters per second. So like the oscillation is so much more than just the net trickle into Huron. And I think that gets at that question of like, how long is water hanging out in there? And Straits really mess things up.
So we talk about all this water and why this is such an important area in terms of the, like, you know, recreation and water hydrodynamicity and all this stuff. But so under there is where this Enbridge Line 5 is. That's where all this oil flows through. And I did look it up. It's about 540,000 barrels a day, which is roughly a Deepwater Horizon oil spill per week of oil going through there. I happen to know because I started working for Sea Grant as a result of the Deepwater Horizon oil spill. Anyway, so is it just the convenient place to put it is there because you can go under the lake as opposed to having to go underground? It's easier, and you have to go through cities and things like that. Do you know why it is they chose that area? Such an important area for the pipeline.
I don't know the reasoning behind that, but my guess is that that's the shortest point to get across, right? So that the least amount of underwater pipeline that they could use to get down to Sarnia. And probably the least amount of pipeline. The other option is to, if you don't want to cross the Great Lakes, is to go on the north side of Superior and down through Ontario that way to Sarnia. And that's probably just a longer route. So the decision is probably like, this is our shortest way in the least amount of underwater, pathway that we got to take.
At NOAA GLERL, you have been involved in some modeling to see like what would happen if there was a rupture in the pipeline, right? And where the water would go based on the types of information you were talking about earlier. Can you tell us a little bit about how the models are created or how they have been created and maybe refined over the years? Yeah,
so it starts really with observations of what's going on with the hydrodynamics. So with that, currents basically, but water levels and temperatures and all the different physical aspects that we care about. And GLERL started measurements in the Straits in the 70s. And there was probably measurements before that by the Army Corps of Engineers, I'm guessing, with maybe the design even of the pipeline. But in the 70s, NOAA made some measurements of currents. They did so again in 1990. No models of the Straits yet in there. And then we started to do it since I've been at GLERL in maybe about 10 years ago. Started taking more measurements of currents and temperatures in the Straits. And that was to get a better sense of really what's happening there. So the measurements in the 70s told us that the flow is oscillating, give us a sense of what that looks like, how often that happens. In the 90s, it confirmed that with kind of a newer technology. But to build a model, we needed a little bit more data, and we needed year-round data. Both of those were just field campaigns that lasted for part of a year, a few months. And so we started putting out measurements to take current measurements throughout the water column at a few different locations in the Straits year-round. So every hour, getting an understanding of what the currents are doing from the bottom of the lake to the top. Same thing with temperatures and other conditions. So that's the kind of stuff that we need to use to, I guess, check the model. But in general, how these models work, these are models that have the basically physics equations, physics processes written into computer code. And we tell, based on what we know about physics, we say, this is how water would react to certain wind conditions or atmospheric conditions. These models then are broken into little chunks, so little pieces that make up the lake surface. So imagine, I guess, picture, say, Lake Michigan, and if you broke it into, a million little triangles, that's what these models look like. And in each one of those triangles, we solve a bunch of physics equations to say how the water will move in reaction to, say, whatever the winds that's happening on the surface. And that's how these models are, so that information is passed from one triangle to the next, and that gives you a prediction of what's going on in the lake. When we do that, we can just trust it, or we can say we better check it against observation. So in this case, we build these models, and then we check them against all kinds of measurements from around the lakes. So not just in the straits, but all over. In the straits in particular, because it's so important to many aspects, and because the currents are there's a lot of action up there, these measurements are really critical to understand if we're getting that component right. And so we use that to check the model if we need to make changes, if there's some mismatch, that it becomes like an investigation. What's wrong with the model? Where's that error coming in, and we try to fix it. It's a continual improvement process that will last well beyond my career. But that's really the backdrop there. So the straits, in context of the Great Lakes as a whole, the Straits is probably one of the most observed locations in the Great Lakes from a physical standpoint. So currents and water temperatures, even waves, we have more data there just in the last few years than we have really anywhere else.
Which sort of makes sense based on how important it seems to be to not just Line 5, like we're talking about Line 5 specifically today, but a bunch of other things too.
So part of the deal with these models is you want to be able to predict what would happen if there were some sort of rupture or spill related to Line 5, right? Is that all you use them for? Or do you use the models for other things related to lake dynamics, etc.?
Great question. So these models are actually designed before we started even considering the Line 5 rupture and the place they would serve there. So NOAA operates these types of hydrodynamic models for the oceans, for coastal oceans, and we have our own set here in the Great Lakes. And these are run in what we call operational mode, which is they're the official model output that gets turned into a forecast. So if you see a forecast for water temperatures or ice or water levels, or there are current forecasts, most people don't look at them, but that comes from these models, and that's part of NOAA's bread and butter is to create these types of forecasts. So we've had these models in the Great Lakes providing real-time information on hydrodynamics for about 20 years. The Straits were a gap there. So until about 10 years ago, our Lake Michigan model just pretended like there was a wall at the Straits of Mackinac, and same with the Lake Huron model. And so we didn't have any means to predict what would happen at the Straits. Our initial effort was to start including the Straits in these models, and so we started taking these observations. And that was only about a year or two before I even heard about Line 5. Kind of in that process of building this model, so we would have forecast conditions for the Coast Guard, for commercial navigation, kind of the more common stakeholders. In that process, somebody approached me and said, there's an oil pipeline down there. And that started the process of really expanding the utility of these models then for things like spill transport.
When you tried to apply these models to, like, if there was a spill, what did you find in terms of if there's a rupture in the pipe that's underneath the water, what would happen? Where would the oil go?
So, because the currents are oscillating back and forth, right? If that waterbed analogy. So it moves on a pretty regular period. Every few days, the water will reverse from one direction to the other in the Straits of Mackinac. But the direction of, if there was a rupture, the direction of the oil depends on when that happens, right? So if the currents are moving eastward, it's going to immediately shoot eastward for a while, and then it's going to reverse and go westward again. And so there's this, initially it all depends on the exact minute or hour of that rupture. But eventually it's going to be spread in both directions. And because the currents are so high there, it's going to make pretty far headway into each lake. I don't have an exact number on top of my head. It kind of depends on the amount of time. If there's a spill response, there's also evaporation, oil on the surface that can happen as well. But well into Michigan, well into Lake Huron, and really quickly too. So, over a matter of a few hours or a couple of days, you're going to have a pretty massive spread in that region.
Do you have a sense of how, and I acknowledge that this is a super tricky issue, and anybody who wants to go out and read about it, there are people who depend on this pipeline for their livelihoods all over the place, and there are lots of people who are saying, the risk of a rupture is too great.
Or the consequence, perhaps, rather than, right? It's a low probability, high consequence thing, isn't it? Or
Right. But I guess, do you have a sense of how different groups have used the information that's available to them through the work that you and your colleagues at Clairol have done?
Yeah. So all this model output, and in fact, these models themselves are, for the public. So these predictions have gone into a spill exercise conducted by Enbridge and by the Coast Guard in 2015, and it was used to, give some estimation of a hypothetical spill and allow them to prepare and respond for that. So it goes to both of those groups. It has gone to studies that have come out of academic partners looking at worst case scenarios of spills and the impacts to the region in various degrees. This is the currents, the model currents that have supported those. So really, I think, I can't say this for certainty, but anytime if you've seen any kind of trajectory or hypothetical spill around the straits, it's probably come from these models, at least the current components. And so that's been given out to everybody. So, that information that gets used for policy, is built on, at least in one component, these types of models, and it used again across industry from different levels of spill responders, Enbridge themselves, and environmental groups too.
And so this is interesting. So you've created this really powerful model, right, that people are using. They use them in exercises, kind of these fire drill or oil drills, I guess, right? You have people using them in industry and government and things like that. So we talk about modeling a lot on this show. And one of the things that I'm always interested in is like how well these models are validated, I think, in the real world. And you sort of alluded to that. But when people have gone through different exercises, or have you done any real world tests? And if so, how is the model done? Or is there ways that you've adapted the model based on real world tests? What on the ground, how well does this seem to work?
Yeah, so part of the design process of these models is initial, we call it a hindcast, right, instead of a forecast. But so going back to a historical year, running that year and comparing it to observations and say, like, how good would the model have done? And NOAA has certain standards that models have to meet in order to become an operational model to provide forecasts. And I should say these forecasts are then what's used. If there was a spill tomorrow, the currents from this model will be guiding spill responders on, how they'll be part of the information they use to decide how to respond. So there's that hindcast piece where we test the model and validate it and go through a vetting phase. Then once it's run in real time, so this model is run every few hours in perpetual forecast real-time conditions, there's ongoing verification. So we have observations out there right now that we can compare to all the time, and that allows us to track if the model starts to drift from reality. Or if there was a spill, responders could look at like how well has the model been tracking in the last few days, and they can use that to provide some amount of confidence in what they might, expect the quality of the forecast to be. The other thing is then we do ongoing campaigns. So we've released drifter buoys in the Straits of Mackinac, which are these little sailing kites that go in the water and they move with the currents, and they have GPS trackers so that satellites can tell us where they go. And then we say, okay, would the model have tracked that, right? If I dropped a hypothetical buoy in the model and allowed it to move, does it move in the same direction as that? And so we're always doing these little tests. And so in that sense, there's continual verification. Improvement also happens. These models are lake models. They're models of the water. The input they need to run is what's happening in the weather. And that's also a NOAA thing. So NOAA is running weather models. So any improvements in weather models over the Great Lakes is essentially passed on to these lake models. So if we get better wind forecasts, say next year, we're going to have better hydrodynamic forecasts next year. And so there's that kind of assembly line style improvement to something that would help, in a spill response.
So we always need more and better computers, essentially, even still.
Right.
And then, so I didn't realize that, like, operational model, that's interesting. It's like a term of art, essentially, right? And that's something that no one needs. I'm reminded of that George Clinton album from the 90s, The Awesome Power of a Fully Operational Mothership. Well, this is really the fully operational model. So that is interesting. The other thing I'm reminded of, so my master's degree is in fisheries biology. I got that at University of Georgia. And the guy I was working with there was studying, I think it was striped bass. And they wanted to study how the eggs would flow through the Savannah River. And there was this, like, the 90s was a time of, like, gimmicky experimental sodas. You had, like, Crystal Pepsi, OK Soda. If anybody remembers calling 1-800-I-FEEL-OK, you could call up and there would be these funny recordings. But there was this other one called Orbit Soda, which was produced by Carolyn's favorite company, Clearly Canadian. And it had, like, these little floating balls in them. And so he figured out that these have the same specific density as striped bass eggs. And so he released a bunch of Orbit Soda into the Savannah River and tracked it that way. So, if you're looking for a new way to validate your models, you might be able to find some old Orbit Soda.
If you can get a permit. Yeah.
Right. We do on occasion have done dye studies, not in the Straits because it would take a massive amount of dye to do much there. The drifter buoys do a decent job. But, it becomes a problem. People see dye, they get concerned that something is wrong, which is, a good reaction to have. And so those are a little bit trickier to do, but those are common in rivers. And so we've done that, in coastlines or St. Clair River, places like that.
Well, Eric, this is really interesting, actually. It's fascinating stuff, and it sounds like important work. And I'd love to hear about kind of the relationship, how government stuff feeds into industry and whatever. It reminds you of the importance of government science. But that's actually not why we invited you here on Teach Me About the Great Lakes today. The reason we invited you on Teach Me About the Great Lakes is to ask two questions. The first of which is this. If you could choose to have a great donut for breakfast or a great sandwich for lunch, which would you choose?
I think a sandwich could do a lot more for me. I think the ceiling on the greatest donut is just too low. And so I'm gonna have to go with sandwich.
That's a great answer. It's totally true, right? So are you in Ann Arbor then at Glarel? Is that where you are? So next time I'm in Ann Arbor, I'm going to visit my friend Maria Lemos, and I'm going to take Maria out to lunch, and I'm going to get a great sandwich. Where should I take Maria out to lunch?
The classic answer is probably Zingerman's Deli, which everybody gives, and that's I support that. I think that would be fun.
Okay, but what's your non-classic answer?
So I used to I haven't been there in a while because of the pandemic, but the Tempeh Reuben at Old Town Tavern.
Yeah.
It's a good place to go.
I love a good Tempeh Reuben. What was the name of that place? There was a place in Gainesville. It went out of business. I guess I was the only one who loved the Tempeh Reuben. But it was... All right. Well, I'm going to go to Old Town Tavern and get myself a Tempeh Reuben.
There you go.
That sounds good. And the second question is this. So you are, and let me get this right, you're a physical scientist, yes, but more specifically, you are a hydrodynamicist. What is it that makes you good at that job, right? What are some key skills for your type of work?
So most of the work revolves around computer modeling and computer programming. So that's like a huge piece of it. And then interest in, the physical side of things. So that's probably the skill set behind that. I think, but I started this job, 13 years ago, I can't remember. And I didn't have a background in this type of stuff. So I was a fluids modeler, but did not work in environmental or Great Lakes or hydrodynamics or anything like that. But I had the modeling and physics skill set and just learned on the job here. So I'd say more so it's like the enthusiasm about those things, right? So if the movement of water through the Straits of Mackinac is exciting, that with some programming skills is the magic recipe, I think.
Well, Dr. Eric Anderson, hydrodynamicist with the Great Lakes Environmental Research Lab, NOAA, in Ann Arbor, right down the street from Zingerman's. Where can people go to find out more about the work that you do? Maybe these models or something like that. Is there a website? Is there a social media feed? Something along those lines? Yeah,
there's both. You can go to glarel.noaa.gov to check out a lot of the research that we're doing here in the Great Lakes. You can also find links then to social media that Glarel and NOAA partners are putting out.
That's perfect. And if you're listening right now, you can go ahead and look at your podcast feed, and we'll have that in the show notes. Or if not, you can go to teachmeaboutthegreatlakes.com/34, number 34, because this is episode 34. Well, Dr. Eric Anderson, thank you so much for coming on and teaching us all about the Great Lakes.
Thanks, Stuart. Thanks, Carolyn. This is great.
Carolyn, I'm so appreciative of you bringing that issue up, Line 5, because I honestly hadn't heard about it until we started talking about it for a potential episode. And I mean, it's in the news right now because there's a big international dispute over whether or not to shut it down. And we're trying to get some guests to even talk about that because I think it touches on so many things that are so important.
Right. Yeah. And I think the deal right now is that the state of Michigan said they have to shut it down. They do have a permit to build a tunnel underneath that, like it would no longer be in the water. So like the company has permit to, I believe they have a permit to basically build an encasing tunnel so that it wouldn't just be in the water and like if somebody strikes it or whatever, it would leak. But it's so tricky for so many different reasons. And it's a huge deal on both sides of the border right now.
Yeah.
So,
yeah.
Yep.
And it's rapidly evolving too. So, but right. It's an issue worth following because it's tricky. It's important. It runs through an environmentally important area and economically and, everything about it's important. But I mean, we're also still an oil-driven society, right?
Right.
And so that's a lot of oil that it brings and a lot of energy and a lot of jobs. So it's if there were easy answers, they would have done those already, I think.
Right, for sure. So what did you learn today?
What did I learn today? I learned just like the basics about Line 5, which I didn't even know, and I learned that the hydrodynamics in the Strait of Mackinac, where the Big Mac Bridge is, are really complicated and interesting and frankly exciting in certain definitions of that word. So I learned a ton. How about you?
Yeah, I mean, I love geeking out about stuff like this. I think everybody who listens knows this by now. But he's also, he's absolutely right that it is a beautiful, beautiful spot. We try to go up there every summer and basically spend a week just sitting and staring, and it's lovely.
Yeah, yep. Sitting and staring. The ultimate goal of parents everywhere is just to get a minute to sit and stare. That's all I want. Great. All right. Well, a couple of announcements. Whereby a couple, I mean one announcement. Teach Me About the Great Lakes Book Club. We've already announced this once or twice, but in case you are unaware of it, we're going to be reading and discussing Dan Egan's Death and Life of the Great Lakes this summer. It's only one book. Sounds like two. It's just one. And so if you want to start, if you want to take part in that book club, go ahead and read it. We're going to be reading it this summer. We're probably talking about it early fall. We're going to tie it in with some work we're doing with some graduate students. But we're going to take listener calls and comments. So go check out the book. Read the book. It's a classic for a reason. Or at least that's what they tell me. I haven't actually read it yet. But I assume it's a classic for a reason. And if not, well, then I'll tell you that. Because, honesty in podcasting, very important.
Absolutely.
Yeah. Anyway, do the thing, Carolyn. Let's get out of here.
All right. Are you going to play music?
I am. I got this loop thing. I'm just going to roll with it. Ready and bada bing, bada boom.
Teach Me About the Great Lakes is brought to you by the fine people at Illinois Indiana Sea Grant. We encourage you to check out the great work we do at iiseagrant.org and at ILINSeagrant on Facebook, Twitter, and other social media. Teach Me About the Great Lakes is produced by Hope Charters, Carolyn Foley, Megan Gunn, and Irene Miles. Ethan Chitty is our associate producer and fixer. Our super fun podcast artwork is by Joel Davenport. The show is edited by the awesome Quinn Rose, who we really appreciate, and I encourage you to check her work out at aspiringrobot.com. If you have a question or comment about the show, please email it to teachmeaboutthegreatLakes@gmail.com or leave a message on our hotline at 765-496-IISG. You can also follow the show on Twitter at Teach Great Lakes. Thanks for listening, and keep grading those lakes.